I'm Snigdha Saha, and I'm excited to share our work on using score-based diffusion models to perform image reconstruction in photoacoustic tomography. Photoacoustic tomography, or PAT, is a promising medical imaging technique that can be used to image tissue and vessels beneath the skin. In this technique, a laser pulse is shined on the object being imaged, and photons from the pulse diffuse into the object's tissue. The absorption of optical energy from the photons causes local temperature rises, leading to pressure buildup. The pressure then propagates as ultrasound waves. This is called the photoacoustic effect. The waves are detected by an array of transducers surrounding the object, and the resulting measurements can be used to reconstruct an image of the object's interior. A main benefit of PAT is it does not involve harmful radiation. It has successfully been used to image the brain, the hand, and also the human breast. Because of the interaction between hemoglobin and light, blood vessels tend to be especially prominent in PAT images. These blood vessel features can be useful for diagnostic purposes, including tumor detection. In a full-ring PAT system, the object being imaged is fully surrounded by transducers. However, due to resource constraints or physical constraints, PAT might have to be done with an incomplete ring. For example, the limited view problem occurs when we can't surround the entire object with transducers. This means that any waves propagating away from the available transducers would be missed. Another setting is the spatial aliasing problem, in which only a few transducers are evenly spaced around the imaging target. In both the limited view and spatial aliasing cases, retrieving an object from imperfect measurements is an ill-posed problem. We call it ill-posed because the measurements are not sufficient to constrain the image reconstruction, meaning there are infinitely many images that would agree with the observed measurements. In our work, we view the task of image reconstruction through the lens of inverse problems. Given an imaging target, such as a human breast, there is a physical sensing system that collects measurements. In PAT, measurements of acoustic pressure are collected over time per transducer. As a reminder, the sensing system consists of a transducer array to detect ultrasound signals emitted due to a laser pulse. In the ill-posed or imperfect measurement setting, we don't have the full transducer array. Yet, from these limited measurements, we would like to reconstruct a plausible image of the object of interest. Because of the ill-posed nature of the problem, imaging must be done with the help of computational methods. Note that our work focuses on 2D imaging, but this method may be extended for 3D in the future. More formally, we can express the sensing operation as a forward model that describes how to map an image to measurements. And imaging can be formulated as an inverse problem. X star denotes the original image, Y is the measurements, and X is a possible image reconstruction. Image solutions can be found as samples from the posterior distribution of possible images X conditioned on the measurements Y. By Bayes' rule, the posterior is proportional to P of Y given X, which is known as the measurement likelihood, times P of X, or the prior. The prior enforces biases on the image reconstruction in order to produce a plausible image. A major question, however, is how to leverage a rich prior for image reconstruction. Traditionally, regularizers, like total variation, have been used to impose basic image assumptions, like spatial smoothness. Here's an example of TV reconstructions of the breast image in question for limited view and spatial aliasing measurements. Clearly, these images are not very plausible or informative. For a more sophisticated prior, we can turn to diffusion models. Diffusion models have become state-of-the-art image generators, for example, generating high-quality and convincing images of celebrity faces. What if we could leverage the prior inside a diffusion model for image reconstruction? At a high level, given a training dataset, we can train a diffusion model to generate images similar to the training data. The generative distribution is denoted by p theta and represents the prior that we would like to incorporate in our inverse problem. In our case, a diffusion model would be trained on synthetic vascular images, Once trained, it would effectively represent a data-driven prior of vascular images. A diffusion model is trained by considering a noising process, whereby each clean image from the training dataset is progressively noised until it approaches a sample from a simple Gaussian distribution. The diffusion model learns to denoise each of these noisy versions of the image. With a trained diffusion model, new samples can be generated by following the reverse direction. Starting with a random Gaussian noise image, we gradually denoise the image with the diffusion model. At time 0, the resulting clean image is a sample from the learned image distribution. The question for us is how to turn a diffusion model into a conditional sampler for PAT data. Given some measurements, say of a ground truth image, we would like to modify the sampling process of a diffusion model to produce possible image reconstructions conditioned on these measurements. This means that we need to incorporate the measurements somehow throughout the sampling process. Previous work by Song and Shen et al. Showed how to do this for certain medical imaging modalities like MRI and CT. However, PAT has a very different type of forward model. Our measurements have a time dimension and cannot be represented in the same type of space as that of MRI or CT. Since PAT is not compatible with this previous method, we set out to develop a way to use diffusion models to solve the PAT imaging problem. Now, let's discuss the method proposed in our paper. We'll now step through our method for conditionally sampling PAT images given measurements of an unknown ground truth. We start by sampling from an image of pure noise from a multivariate Gaussian distribution. We then slightly update the image by imposing measurement consistency. Note that we manually add random noise to the measurements to match the noise level of the image. Next, we apply the learned diffusion model to slightly denoise the image and give us the image at the next time step. This denoising step corresponds to imposing the learned prior. Again, we impose measurement consistency and then denoise the image. We keep doing this iterative process, and then at a smaller time t, you can see that the image is much less noisy. Once t is about 0, we have a clean image that is consistent with both the prior as well as the measurements. We output this final image as a conditional sample to solve the inverse problem. Let's zoom into one step of the sampling process. In the beginning, we have xt, which is our current noisy image. We wish to incorporate the noisy measurements, yt, somehow in order to update that image to xt. We wanted to make the measurement conditioning more general than that of Song et al., so we developed a formulation that supports any inverse problem with a linear forward model. To figure out how to update xt, we solved this optimization problem, where z is our image decision variable, xt is the current noisy image, yt is the current noisy measurements, and a is our forward model. In our case, we are able to approximate the PAT forward model as a matrix through a method known as curve-driven model matrix inversion, or CDMMI. Lambda is a hyperparameter that determines how much to weight this measurement objective. This optimization objective resembles regularized maximum likelihood, where the first term in the objective corresponds to the prior, and the second term corresponds to the measurement likelihood. The solution, xt prime, is the updated image at time t. It turns out that this optimization problem has a nice closed-form solution. Our sampling algorithm consists of iteratively updating xt with this measurement conditioning formula and then applying the diffusion model to denoise the image. To recap, we start with an image of pure noise at time t equals 1. We iteratively apply the measurement conditioning formula and then apply the diffusion model to denoise the image. After enough of these steps, we have a clean image reconstruction. Notice that a crucial advantage of our approach is that it can give infinitely many samples by changing the random seed. This helps give a sense of uncertainty in addition to single image reconstructions. Here's a video showing how the image looks throughout the sampling process. For most of the time steps, the image looks like pure noise to the human eye, so we have only included the latter half of the sampling process here. Now we will show some results from our experiments. For our experiments, we trained a diffusion model on a dataset of images of synthetic vascular structures, with the aim of using this as our prior for PAT image reconstruction of blood vessel images. We used a software called VascuSynth to generate a dataset of 9,900 training images, 2,000 validation images, and 100 test images. We tested our method in simulation on various measurement configurations. First, for limited view, we tested 3 scenarios. One where you have 74% coverage of the circumference, one where you have 50%, and one where you only have 26%. For the spatial aliasing problem, we tested 50%, 33%, and 25% coverage, all with the transducers evenly spaced around the circumference. In this talk, we'll show results for the hardest scenarios in these 2 categories. We compared to 2 baselines. The first is total variation, or TV regularization, which imposes a relatively weak prior. We use the FISTA algorithm for imposing TV regularization, and here's an example of TV regularization for denoising. As you can see in the denoised image, TV essentially prefers smooth regions in the image. We also wanted to compare to a fully supervised learning approach, where we train a neural network to directly output image reconstructions, given naive reconstructions from the measurements. The method we compared to was sparse artifact UNet, which was proposed in 2019. The input to the UNet is a naive reconstruction from the measurements using Tikhonov regularization. The output is hopefully a clean version of that image. Note that this method requires paired training data. Unlike our method, it also needs to be retrained for every new measurement setting. So for our experiments, we had to train 6 different UNets to handle the 6 different measurement scenarios we considered. Let's take a look at some results, starting with the limited view setting with 50% coverage. Our method outperforms both baselines, even the fully supervised method. An even better PSNR can be obtained by taking the empirical mean of our samples. Here's limited view with 26% coverage, which is a more difficult setting. TV regularization misses a lot of the detail in the region of the image that would be far away from the transducers we have available. The end-to-end UNet has good perceptual quality because it was trained on paired data for exactly this measurement setting. Still, you can see that one of the samples from our method has reasonable perceptual quality, and the mean has similar PSNR. Furthermore, unlike the other 2 baselines, we can get many samples from our method and look at the pixel-wise standard deviation. The magnitude of the standard deviation has increased, and most of the uncertainty is in the bottom region of the image that would be far away from the observing transducers. Hallucinations from the prior tend to appear in this region of high uncertainty. Now let's look at an example of spatial aliasing with 25% coverage. Notice how the TV reconstruction has streak artifacts. Our method does perceptually better than the end-to-end UNet here and outperforms in terms of PSNR. If we zoom into these images, we see that there are high detail features in our reconstructions that do not appear in the TV or end-to-end baseline results. For a quantitative analysis, we performed image reconstruction on the test set of 100 images. Across all 3 spatial aliasing configurations, we found significant improvement over the baselines. As for the 3 limited view configurations, we found that our method performed on par with the end-to-end baseline. The empirical mean of our samples yields a significant improvement even over the end-to-end baseline. In our paper, we show a similar trend for the SSIM, or structural similarity metric. Recall that there is a measurement weight hyperparameter, lambda, in the measurement conditioning formula. We tested the effect of changing lambda in both the limited view 50% and spatial aliasing 33% settings. Intuitively, the higher the value of lambda, the more the image is constrained by the measurements, and the lower the value of lambda, the more the image looks like a random sample from the prior. In the plot, the x-axis represents decreasing 1 minus lambda. So as you move to the right, the measurement weight increases. We see that there is a gradual improvement in PSNR as we increase the measurement weight towards 1 minus 5 times 10 to the negative 8, past which there is a drop in performance. This suggests that we don't want to weigh the measurements too much and overpower the prior. Here's an example of how a reconstructed sample changes as lambda increases. Notice that for the first image, which has the lowest measurement weight, there are some hallucinated features, presumably from the prior. The middle image shows the best lambda in terms of PSNR. If we increase the lambda too much, the image becomes less likely under the prior. One advantage over the end-to-end learning approach is flexibility. Given the same diffusion model prior, we can perform image reconstruction for different measurement settings. In this experiment, we simulated measurements for the 50% limited view setting. For the baseline, we reconstructed an image using a unit trained on the spatial aliasing setting. Using our approach, we could apply the same diffusion model that we've been using for all the different measurement settings. Because the unit was trained on a different distribution of paired data, it performs worse in terms of PSNR and may miss out on features in the ground truth, such as the branch shown in the zoom-in. We also demonstrate the flexibility of our method by reconstructing an out-of-distribution image of a real breast. For this experiment, we simulated measurements of a reconstructed image of a real breast, which was obtained by a high-fidelity PAT system. Our approach was able to get good performance without any additional training. In contrast, the end-to-end baseline struggles with this out-of-distribution image, even though it was trained for the same measurement setting. We performed the same experiment for spatial aliasing with 25% coverage. Again, we see that our model achieves better qualitative and quantitative performance without additional training. To summarize, photoacoustic tomography is a promising, relatively safe medical imaging technique. But image reconstruction becomes ill-posed in the limited view and spatial aliasing measurement settings. We proposed a way to use a pre-trained diffusion model as a prior to do ill-posed PAT image reconstruction. The key to the method is a measurement conditioning formula that's used throughout the sampling process of the diffusion model. That formula, unlike that of Song and Shen et al., works with any linear forward model. In experiments with synthetic vascular images, we demonstrated substantial improvement over TV regularization and competitive performance to a fully supervised method. The advantage of our method is that it is unsupervised and flexible. Thus, it is adaptable to new measurement conditions. Our work establishes a promising path to leveraging deep learned priors for flexible PAT imaging. It would be exciting to test this method on real in vivo data instead of simulated data. Another exciting step would be to impose 3D diffusion model priors to reconstruct a whole volume. Thanks for listening.